there, welcome to our next video on here. This one has to do with projectile motion. So we're going to take some of the things that we have learned about kinematics, as well as force and force vectors, and we're going to combine them together to be able to analyze what happens when we chuck stuff off a cliff. Projectile motion. So first thing first, what's projectile motion? By definition, projectile motion is any situation where really the only force that's affecting the object's motion is the force of gravity. That's it. Once we have launched, say, the cannonball that's in there, yes, there was an initial force to get it moving, but as soon as that cannonball exits the cannon itself, it is then only being governed by gravity and inertia, right? So it's got some initial movement to it. It's kind of maintaining that. But other than that, that's it. It's not something that's continually being pushed. So we can talk about projectile motion, throwing things straight up in the air, throwing things at an angle, dropping things off of a cliff, or shooting things off of a cliff like this. But it's anything where really the only force that is acting on that object's motion at the time is gravity. And that's kind of the key defining characteristic of how we know what this sort of motion is. So with this, I'll get my pen going here so I can actually get the right color going. There we go. So with this, come on. There's an important thing to kind of keep in mind with this. Our arc, the name of this arc right here, the trajectory, if you want to call that, the shape of that arc is a parabola. And it's always at least a half of a parabola like this, where it's just going downwards. If you're shooting it up first, then you'll get the full parabola or parabolic arc if you really want to. But that's the name of the shape. Trajectory is the general name of a path. Like any projectile travels along a trajectory, nice English. But the shape of the trajectory is parabolic or a parabola. When we are analyzing the motion of this, we can take into account our information that we have about vector components, and we can actually use that concept to analyze the motion of any projectile. We can take into account, or we can use the idea that the vertical motion is actually in many ways completely unattached from the horizontal motion. So what we see here is vertically, if we were to just say, drop this cannonball off the cliff, it's literally just going to go straight down. And we could actually kind of figure out what that was. There'd be acceleration due to gravity, and it would kind of, start here, and then it would fall, and then it would fall a little further and fall a little further yet. But horizontally, what's the force that's playing on it? So again, horizontally only. You can't think about the gravity part of it. Well, horizontally, the only thing that's impacting this object's motion was its initial velocity. It's literally undergoing inertia and inertia only. It's not accelerating at all in the horizontal path. Once that initial push, it's called impulse, was used to get that thing out of there, and now it's moving, it's sort of coasting horizontally. That's what they call the gravity-free path. And you can kind of see that along this gravity-free path, that it's moving constant velocity, same amount of displacement in each horizontal instant of time. Vertically, it's accelerating, right? So it's starting, where's my pen? It's starting like here, and then the second one is about here, and then the third one's about here, and then the fourth one's about there. I'm lining up these dots with these ones over here, right? So horizontally, you can see it's going a constant interval, but vertically, where'd it go? There, and where'd the rest of them go? There, and there. So this direction, the vertical sense, they are indeed accelerating as we go. Do I have I must have the magic pen, and it's disappearing as I go. Sorry about that. Let's try that one. There we go. So again, two different motions. So how do we analyze these things? Okay, the trick is to analyze the horizontal component and the vertical component as though they are separate problems. And then we're going to have a way to sort of bridge the two ideas. So number one, when we're dealing with the motion on this, I was just talking about this, the horizontal component of this is simply constant velocity, only inertia. Again, after the initial push to get it moving, it is now coasting horizontally across space. That means that the velocity is staying constant as it's moving horizontally. So your initial velocity in the x direction is equal to its final velocity in the x direction. And when we're using our labels and stuff in this particular unit, it's really important to make sure you're clearly thinking, is this horizontal or vertical motion? So we're only talking about horizontal motion, so we're going to put that x in there, and that's super important, because otherwise, as you're doing all your math and they're all kind of like x's and y's and vi's and vf's, hard to sometimes remember, was that a vertical or horizontal? Most important thing, again, that students do is they get those two components sort of mixed and matched. So horizontally, there is no acceleration. Therefore, because there's no acceleration, we can actually use this equation. Velocity is distance divided by time. We can use that because there is no acceleration horizontally. Vertically, there is definitely acceleration, so you cannot use this thing vertically, but horizontally, this is the equation that you're going to end up using. Now, the good news, what do these things mean? Well, Vx here, that's its initial horizontal velocity is equal to its final horizontal velocity. That's what Vx is. And then dx is the distance that it travels horizontally. In other words, how far away is it going to hit the ground? How far away horizontally? It's also known as range. So what is the range of this projectile? Basically, that would be the distance from here to wherever that final spot is. This would be dx. And in other words, the range. It's almost always considered to be a positive value. So again, for the horizontal motion, we can use constant velocity equation. Velocity is distance divided by time. Vertically, when we take a look at the vertical motion, now we do have acceleration in the vertical motion because the vertical motion of this object is 100% governed by gravity, acceleration due to gravity. It's like a free fall problem, and that's how we're going to kind of deal with these. Where we're talking about our free fall here, acceleration in the y direction is equal to acceleration due to gravity, or negative 9.81 meters per second. Again, if we assume that the down direction is the negative direction, which is what typically people do. And that's fine if you don't. But again, I'm going to do mine in that particular sense right now. So if we talk about this falling version of it, we've got acceleration is equal to negative 9.81. A couple other things to keep in mind. Now, because we're using acceleration, we're going to be dealing with our kinematics equations. The only difference between these kinematic equations and when we looked at them in the previous chapters is now we have y's in there. Because again, we are now only talking about the vertical component of its motion. So we're talking about the y direction, not the x component. Remember the x component, constant velocity. So that's why we have vfy and viy, because we're talking about the vertical components of this. And then a is going to be our acceleration due to gravity. dy is going to be our change in elevation typically. It could be height if you're throwing it up. It could be elevation. It could be the amount of fall, but that's our vertical dimension. It's usually negative as well. Again, if we have negative 9.81 for acceleration, then delta D, the change in displacement downwards, is also a negative value because you're going in the negative direction. So again, if you want to flip those and make them all positive, that's up to you. But that's a different, I'm not going to do that in these just to keep it consistent. So again, usually our change in displacement, our delta D, is downwards, which is the negative direction. So again, height, elevation, or fall. So let's take a look at how we combine these two things together. Oh, and by the way, typically in problems like this, they're going to ask you questions like, what is the range of this projectile? What was the maximum elevation that this thing could have hit? Something along those lines. They're not going to ask you to do the final, I guess they could ask you what the final a resultant vector is. Like they could ask you what the sum of those velocities were at the angle, but that's a more unusual kind of a problem. Usually they just kind of want to know how far is it going to fall, when's it going to get to the ground, or how far away is it going to hit. So how do we solve problems like this? The trick here is, again, number one, make sure you're looking at the two different components, the horizontal component, the vertical component. Horizontal component is all about constant velocity, again, not changing as it goes from left to right. Vertically is our kinematics, which is generally all about doing acceleration due to gravity. And then the one piece that we have that can actually communicate between the horizontal and the vertical dimensions is time. Right? Whatever time it takes to hit the ground vertically is the same amount of time that it takes to hit vertically. So I know it sounds kind of funny to say it. If we had Tx, it would have to equal Ty. They're the same bit. So when we've got time in the horizontal equations, time in the vertical equations, it's the same amount of time. There's no possible way they could do something different. So generally what we do is we solve for one of the two components, either horizontal or vertical, whichever information we have more of, solve for time, and then use time to plug into the other system. So again, it depends on what you're given first. But say, for example, I know some information about its horizontal movement. I would plug in my horizontal velocity and I would know where it was going to land. I'd solve for time here, take this time, and then plug it into my vertical equations and solve for something, a displacement or something like that over there. So again, almost always you're solving for time and translate using that time to go from the horizontal to the vertical. So let's apply this and see what this looks like. So here's an example of our problem here. We've got a projectile launched horizontally off of a cliff at an initial velocity of 8.3 meters per second, kind of like the cannonball problem. If the cliff is 125 meters tall, how far away will the object land? So we're going to start by sketching this here. I'm going to sketch it in this spot, and then I'll end up moving it out of the way. So here's what we got. We've got our projectile is being launched. It's being launched horizontally. So that means its VI is horizontal. That's X. Okay. It's going to eventually fall. Yes, its trajectory is going to eventually be that horrible parabola. So, but again, our VI is given to us. We also know that the cliff, and VIX equals 8.3 meters per second. Again, that's its horizontal velocity, 8.3 meters per second. Okay, if the cliff is 125 meters tall, okay, well, that's this height right here. So that is going to be from here to here is 125 meters. So again, it's falling 125 meters. So our displacement downwards is going to be negative 125, and that is in the y direction. So dy here is going to be negative 125 meters. It's falling 125 meters. We're trying to find dx. That's our question mark. Because again, how far away will the object land? It's asking for the range. And then there's some other pieces that we can figure out about this. All right, so what else do we know about our materials? So this is what we're trying to find. That's our end goal. What about VIY? Okay, VIX horizontally is 8.3, but what about vertically? Okay, this is essentially the same as dropping it off of a cliff. Again, all of its initial speed is horizontally. It has no initial vertical component to its speed. And again, this is one of those things that's sort of hidden in the problem. Our VIY is 0 meters per second. Again, it's like a free fall problem, and that initial velocity when you drop it vertically is 0. Yes, I know it's going horizontally. I'm talking about the vertical dimension of it. How about acceleration? Well, there is no horizontal acceleration. That's going to be constant. Which also, by the way, this equals VFY, right? It's not going to change, or sorry, VFX, pardon me. VF, horizontally, it's not going to change. AY, this is going to be falling. Again, vertical direction, Y direction. This means it's accelerating downwards due to gravity. And the acceleration due to gravity is negative 9.81 meters per second squared. Again, we're going to call this direction as the negative direction. Time we don't have yet. So now we kind of know our components here. So what do we know more of? All right, well, we either have to solve the vertical or the horizontal. We're trying to eventually find horizontal. So for our horizontal distance, horizontally, we're going to eventually use this one. Vx equals dx over t. Velocity is distance divided by time horizontally. We've got the Vx. We're solving for dx. That's actually what we're looking for. But we need to find time. Ain't got no time for that yet. So that means we're now going to need to use some of our vertical information and focus there first. Again, if our final question is asking about a horizontal component, probably going to solve for the vertical component first. So let's take a look. What do we know vertically? So I'm going to kind of erase some of this stuff so we can kind of figure out all of that part. All right. Can I get rid of this, Okay, vertically, what do we know? Well, vertically, we know D. We know VIY equals 0. We do not know VF, but we do know D equals negative 125. We know A equals negative 9.81. Again, this is vertically, so Y. And then we want to find time. We have to use an equation with time in it because our goal is to get time to use in this equation up above. So we have to do an equation with time. We only have 2 equations with time, right? VF equals VI plus A delta T, and df equals di plus vi delta t plus 1/2 at squared. We're not going to use this one. Vf squared equals vi squared plus 2a delta d if we don't have to, simply because this one doesn't have time in it, and we need to find time. Yes, it would allow us to find final velocity, but we don't really quite need it in this particular equation. So we're not going to use this one. We'll get rid of that. What we're really trying to find is, what do we know? VI, dy, and AY. That means we're going to use the second equation right here. We don't know what VF is. Yes, you could do that problem first if you wanted to and do a 2-step, but we can do it in 1 step. So we're going to do this equation right here to figure out what time is. I think that's what we're going to try to solve for. So plug your numbers in and chug. DF, by the way, okay, if we're talking about DF, what do we got here? DI and DF, how do you want to count this? A lot of times what students will do is say DI is 125 meters and DF on the ground is equal to 0 meters. That works. That works. So if you want to do that, that's fine. It's not that our DF is negative 125. It's just going in the negative direction. So we want to make sure that we get our initial minus final to get our delta D to be the right direction. So DF is going to be 0. DI was 125 meters up. VI is equal to 0. Remember, we're dropping it. We're dropping it. That's what saves us in these problems. Plus 1/2 times negative 9.81 times t squared. Again, sorry, mine's on the kind of funky angle there. So our final change in velocity, 125, equals, again, I'm kind of algebra, I went over this direction. So I move my 125 over to the other side. 9.81 times 0.5 is 4.905. Negative 4.905 times t squared. And that's this. So now t squared, 125 divided by 4.905 is equal to 25.484 and some change. Don't forget to take your square root. Second square root of my answer. That means our time here is 5.05 seconds. And I'll go check sig figs here in a second. Looks like we have 2 sig figs to work with. Okay, so again, makes 5 seconds to hit the ground. So then what? Well, once we know what time is, then we can put that up in our top equation. Vx equals dx over t. So again, what is that? Vx times t equals dx. I'm just rearranging it. So we know what Vx is. Vx is the horizontal speed. Vx is equal to 8.3 meters per second squared. Times our time, 5.05. So I guess it would be 5.0. 5 is equal to our d in the x direction. So 8.3 times 5.05 gives us a final answer of 41.8999 or something along those lines. With 2 sig figs, it's basically are essentially 42 meters away. So again, problem-solving strategies. You're almost always going to solve for time, almost always. So decide, do you solve the vertical or the horizontal component first? Depends on what you're given information about. In this case, we were given information about its horizontal velocity. So I solved, get information about horizontal velocity, and I'm trying to find its horizontal distance, how far away. Therefore, I knew that was going to be my last equation. I know it sounds funny to say that, but that's going to be the last one. If I'm asking how far away is it going to fall, dx, that's going to be the last thing that I do. So that meant since it was solving for something horizontal for my final problem, I did the vertical component first. And I did my vertical components. I chose a kinematics equation that worked for that, plugged in my values. Be a little bit careful how you enter your displacements, your distances, to make sure that your change in d is negative. So again, negative 125. And then you're just solving for time. Use the time to plug into your first equation in your horizontal component. And then you can just solve for it, right? Easy as mud. Let's take a look at one more equation. So this is one that you can probably hit pause on. This would be a really good time for you to hit pause and see if you can start putting this one together. Similar kind of problem. So we've got a pitcher throwing a baseball horizontally from the mound to home plate. The ball falls 0.926 meters by the time it reaches home plate, 18.3 meters away. How fast was the pitcher's pitch? So again, this is a good spot for you to hit pause, see if you can draw it, and then I'll identify variables, and then we'll come back and plug in the numbers. So like I said, this would be a good time for you to practice doing an example of a horizontal motion for projectiles. Okay, so here it is. Here's my little drawing. Here's my dude. He's throwing the ball. It's going this direction. So if I could get that to go horizontal, that'd be a little bit nicer. But he's going horizontal motion this way. And again, the ball is going to be going that direction. It's going to be falling as it goes. We know some things about it. We know that it falls this direction. dy is equal to negative 926. It's falling, right? Starts up at 0 or starts at 0.926 and falls to 0, if you want to call it that way, but it's falling that many meters. We want to know at how fast will the pitcher's pitch. We want to know VIX. That's what we're trying to find. We want to know how fast is he throwing it horizontally, because we know it's going to fall. What else do we know? Home plate, 18.3 meters away. So we know this right here, our range, dx equals 18.3 meters. Okay. And then we know some other things about it that are kind of hidden. So we know VIX, that's what we're trying to find. So if we're trying to solve for this, that means the horizontal component will be the last thing that we look at. We're going to have to solve vertically first. Okay, VIY. Again, vertically. What's its initial velocity vertically? 0 meters per second. Again, because I'm throwing it horizontally, it's starting at 0 meters per second vertically and is going to be falling down from there. AY, negative 9.81 meters per second squared, down, right? DX, the horizontal displacement, is 18.3 meters. Again, that's positive. It's going in the positive direction. DY, it's falling. So it's falling 0.926 meters. And time is going to be something that we have to find. Again, always, you're always going to find time in one dimension and solve it for the other dimension. So again, because we're trying to find dx or VIX, that means that we're going to have to solve the vertical component first. Since we know that we're trying to end in the horizontal component, we need to start in the vertical component. So we're going to try to solve in here and kind of figure out what we're going on. So we're going to use our vertical component to find time. So let me erase. So how can we find time in this case? What do we know? This is where we have to pick one of our kinematics equations. So our couple of kinematics equations that we have, VF equals VI plus A delta T, and DF equals DI plus VI delta T plus 1/2 AT squared. Again, we have to use one of these because we need time. Well, we don't know anything about its final velocity. So generally, we don't use that equation. This is almost always the equation that we use. So DF, it's going to land on the ground. DI, it started at 0.9226, not 962, 926 meters up in the air. 926 meters. Our VI is equal to 0, so that whole VI delta T equals 0, plus 1/2 times negative 9.81 times T squared. And by the way, it is just the T squared, not the acceleration of the T squared. So, once again, negative 0.926, our delta y, I guess, if you want to think of it that way, meters is equal to negative 4.905 T squared. You'll get used to seeing this number over and over again. We use it a lot in this particular chapter. So 0.926 divided by 4.905. I'm just doing the algebra now to solve for T. I get T squared is equal to 0.18878 and some more. So I'm going to take the square root. Don't forget to take your square root. And my T equals plus or minus, but it has to be plus because you can't have negative time. 0.4, we got 3 sig figs, 0.434 seconds. Okay, that's our vertical time. Because all of this, what we're doing here, I've got acceleration here, is vertical. So that's our vertical time. So now I know 0.434 seconds. That's when it hits the ground vertically. That also means that's when it hits the ground horizontally. So now I can use velocity equals distance divided by time for the x dimension. Again, now I'm only talking about the x case. We're trying to solve for VIX. We don't know what that is. We do know what our displacement is. Our horizontal displacement is 18.3 meters. And we know that it was in the air for 0.434 seconds. So 18.3 divided by 0.434 is equal to a VIX of 42.2.1658, something like that, meters per second. Again, that's positive because you're throwing it in the positive direction. So that's VIX, or its initial horizontal velocity. So there you go. That's it for this particular video, taking a look at trying to figure out how to solve projectile motion problems. So this one's only horizontal projectiles. So the key points is to realize that horizontal and vertical are completely independent of one another. Horizontal motion is only based on constant velocity, inertia basically. Velocity is distance divided by time. Vertical motion is governed by acceleration due to gravity. So we have to use our kinematics equations for that, negative 9.81 meters per second squared, vertical acceleration. And that time is the thing that goes back and forth between the two. When we solve for time in the horizontal, we know what the time is in the vertical and vice versa. Last hint, if your question is asking you for something that's in the horizontal component, then you know you got to start with solving the vertical component, and that'll save you a little bit of time. All right. So our second video here will be talking about what happens if we launch them up at an angle. Okay. See you there. Have a great one, you guys. Bye.